Hey everyone, so today we are, I am working with the, going over problems from, to prepare you for the ISTEP 10, which is coming up pretty soon, and at least the retake is coming up pretty soon. So what I have done is I put together a packet of problems that I found offline on the internet, on the Indiana Department of Education website. So these are all problems that correspond to standards that are being tested on the ISTEP 10 for graduation, the graduation qualifying exam in the state of Indiana. And these are all problems that are from the that are notated as being critical concepts. So I'm not going to be going over every single standard in the number sense, expressions, and computation area. I'm just going over problems that are from the critical content. So if you are trying to do last minute studying for the Indiana ISTEP, this is a good review for you. And I'm going to make up, I think, 6 different videos, one for each different concept. So the first concept is number sense expressions and computation. So in our first example, or number 1, it's asking to give 2 examples of rational numbers and 2 examples of irrational numbers. So a rational number is any number that can be written as a fraction of integers, which is a positive or negative whole number. So a good example would be something like 2/3. Or if you have something that's a repeating decimal, 0.37 repeating. Any type of repeating decimal, any fraction, any whole number, so you could have a whole number like 5. Those are all rational numbers. An irrational number would be something like pi, which most people are familiar with. It's a decimal, or it's a number that has a decimal that continues forever and ever without repeating. But you could also have a number like 2 square root of 3. So even though there's a 2 in front, because it's with the square root of 3, the square root of 3 is irrational because it goes, again, is a decimal that goes on forever and ever without repeating. However, if you did have a perfect square under the radical, for example, square root of 4, that would now be on the rational side because that's a perfect square and the square root of 4 does equal 2. So these are examples of irrational numbers, or rational, and these are some examples of irrational. Okay, so to describe how to determine whether they are rational or irrational, again, I was mentioning that a rational number can be written as a fraction of integers. And an irrational number cannot. So you cannot write an irrational number as a fraction of integers, where a rational number can be written as a fraction of integers, and irrational cannot. Okay, another problem that you may have to rewrite, or you may have to might be asked, is to convert something that's a repeating decimal as to a fraction. So if you have one repeating decimal, for example, I'm just going to say point n with a line over it. So n is any number. So if you have one repeating decimal, it's going to equal n over 9. Switch colors here a little bit. So for example, if you have something like 0.2 repeating, that's going to equal 2/9. Well, if you have 2 digits repeating, so when you have 2 digits repeating, you're going to take those 2 numbers and put them over 99. So 0.23 repeating would be 23 over 99 If you were to take your calculator and divide 23 by 99, you would see that 0.23, the 2 and the 3 do repeat over and over again. So that's how you convert a repeating decimal of this type to a fraction. So if it's 1 repeating decimal, it's over 9. If it's 2 repeating decimals, over 99. All right. Number 2, letter A. Vita earned $150 last week, and Jay earned $130 last week. They combined their money and decided to donate a fourth of their total amount to a charity. Then they spent 40% of the remaining amount at an amusement park. Jay claims that they only have 35% of the original combined total left. Is Jay's claim correct? So there's a lot of computation going on here, and that's exactly what this question is assessing. So Vita earned $1,500, Jay earned $130. They combined their money and then decided to donate 1/4 of their total amount to charity. So I'm going to stop right there. So the first step is to add these numbers together, and I'm going to use the space over here in the margin. So 150 and 130 added together gives us 280. So that's the total amount that they would have together. Well, if they have 1/4, if they donate 1/4 of it to charity, you could take, now this would probably be a calculator problem. So if you take 1/4 of 280, you basically just have to multiply 280 by 1/4, or you can divide 280 by 4, and you get $70. So you're going to subtract $70. So this is 1/4 of the 280. So $70 is 1/4 of the 280. So that's going to go to charity. So when I subtract, they now have $210 left. So then we'll go on and read that they, the next part, they said they spend 40% of the remaining amount at an amusement park. So 40% of the remaining amount. Well, 210 is the remaining amount. So if I'm taking 40% of that, 40% of $210 would be 0.4 times 210. 0.4 times 210 gives me $84 now that I have left. Or no, $84 is what they spent at the amusement park. Okay, so they spent that at the amusement park. All right, so after they spent the 40% or $84 at the amusement park, let's see how much they have left. So take your 210 minus your 84, and that gives you $126 left. So Jay claims that they only have 35% of the original amount left. So now we need to figure out, well, what is 35% of the original combined total? Well, the original combined total was 280. So if we try to figure out what 35% of 280 is, you could take 0.35 times 280, and that's going to equal $98. So Jay claims that they have only 35% of the original amount, which would be $98. But that is not true. They actually have $126 left. So is Jay's claim correct? Let's see. So in here I've got to write some sort of explanation. No, Jay's claim is not correct. They have $126 left, which is more than 35% of the original amount. So there's my answer and my explanation. And here's all my work to back up what I did. So on the ISTEP, you always want to make sure that you've got the work to back up and support your answer or your claim. All right, moving on to problem B. It says you installed a bookshelf on a wall to organize some books. The books you have to file on the shelf weigh a total of 7.5 pounds. The bookshelf can handle no more than 10 pounds. You plan on filling the rest of the shelf with hardback books that weigh 1/4 of a pound each. So I probably should have put each. So each book that you're adding, hardback book, weighs 1/4 of a pound each. Assuming you won't run out of room, how many hardback books can you add to the shelf? All right, so there's a lot of steps going on here, but the bookshelf can handle no more than 10 pounds is probably an important piece of information. We also know that you already have the books you already have on the shelf weigh 7.5 pounds. So that 7.5 pounds plus the, so this is what you already have. And then each hardback book that you add to the shelf, so you plan on filling the shelf with hardback books that weigh 1/4 of a pound each. So if you would like, that 1/2 is probably easy enough to change to a decimal. That might be easier to work with. So 7.5, make it 7.5. And then the 1/4, I'm going to make that a decimal also, 0.25. But then I'm going to say H. So I'm going to put a variable with that where H is representing the number of hardback books that you're adding to the shelf. So this is your hardback books. Now if you were had to define the variable, you would not just want to say H equals hardback books. You would want to say H equals the number of hardback books. So if you take the number of hardback books times the 0.25, because they're 1/4 pound each, then you will get your weight. And then it says no more than. So if it cannot be more than 10 pounds, then it has to be less than. However, if you read this expression and you think about what it's saying, if it says no more than 10 pounds, could it equal 10 pounds? Yes, it could actually equal 10 pounds also. So here's the inequality that I would have set up. So the 7.5 pounds I already have plus the 0.25 or 1/4 of a pound per hardback book, that total amount has to be less than or equal to 10. So now that I have my inequality, I can answer the question, how many hardback books can you add to the shelf? So over here, I'm going to take my inequality and solve it. So my first step in solving would be to subtract the 7.5, which will be 0.25h less than or equal to 2.5. So 10 minus 7.5 is 2.5. And then I would divide that by 0.25. So when you take 2.5 divided by 0.25, you actually get 10. So how many hardback books can you add to the bookshelf? At most 10. So you can add any number of books that are less than or equal to 10. But if they wanted the most, what's the most number of books that you could add to the shelf, you would say 10. And there we have it. There's our second, our number 2, problem B. All right, the number 3 problems, we have a bunch of factoring going on here. So the first factoring, expression here, r squared minus 121, is a difference of squares. So we've got r squared, which is a perfect square, 121, which is a perfect square, but you have a minus sign in between. So that difference of squares can be factored into r and r, because the first term here times the first term here has to equal the first term here. So r times r is r squared. These two terms here have to multiply together to equal 121. And we're just going to use 11 and 11. but in order to get a negative 121, one of them must be positive and one of them must be negative. So when you factor difference of squares, take the square root of the first term and put it in front, the square root of the second term, put it here, but your signs have to be different. Well, why? So if you were to, so these are the factors, that is your answer. But if you're checking it, if you could multiply it back together. So the r times the r does equal the r squared. The r times the negative 11 would be a negative 11r, so I'm just going to write that off to the side. The positive 11 times r is a positive 11r, so those middle terms cancel out, which is why there is no middle term in your expression here. And then your positive 11 times the negative 11 is negative 121. So these are the factors, and we did check it. All right, the next one, problem B, there are, if you, there's a couple ways you could do this. You could try to use the AC method. However, we're going to use guess and check method. What I've noticed here, though, is that we've got a perfect square here and a perfect square here. So the first thing I'm going to try is factoring it into two binomials where the first terms are the square root of this 144y squared. So if I take the square root of 144y squared, I get 12y and 12y. So these two first terms multiplied together do equal 144y squared. The 25 is my last term, so these two numbers in the binomials have to multiply together to equal a positive 25. So I'm going to just try 5 and 5. Now looking at my signs, since this middle term is negative and this last term is positive, the only way that we're going to get a positive 25 here is if our signs are the same. But the only way we're going to get a negative in the middle is if they are both negative. So this is my guess that it's going to be 12y minus 5 times another 12y minus 5. Well, how do I know for sure that that's going to work? Well, I know that the first terms multiplied together to give me the 144y squared. The last terms multiplied together give me the positive 25. But in order to figure out your middle term, you have to multiply the outside terms and the inside terms. So if I multiply the outside terms together, off to the side, I'm going to write that down. That would be negative 60y. If I multiply the inside terms together, the negative 5 times the 12y would also give me a negative 60y. And if I combined those, that's where I get the negative 120y from. So since this would multiply out to equal the same thing, these are the correct factors. Now, one thing you could do, one more thing you could do, because these are both identical, signs and all, where these look the same but their signs are not the same. These actually are exactly the same. If you two have two binomials that are exactly the same, it can be rewritten as a binomial squared. So 12y minus 5 squared is the same as 12y minus 5 times another 12y minus 5. All right, problem C. Well, the first thing I notice about problem C is that we have a negative in front. And when we factor, I always tell my students, factor out that negative, that if your leading coefficient has a negative number, factor out the negative. But the other thing that I'm noticing is that all of these can be divided by 2. And if I try to think if there's anything bigger than that, no. So the greatest common factor is 2, but I'm also going to factor out a negative with that 2. So if I factor negative 2 out from all three of these terms, and when you're factoring out, whatever's left is what you get when you divide. So dividing that negative 18x squared by negative 2 will give me a positive 9x squared. Dividing the negative 60x by negative 2 will give me a positive 30x. And then dividing the negative 50 by negative 2 will give me a positive 25. So once again, I'm noticing I could use AC method, but the first and last terms, again, are perfect squares, kind of like these ones were here. So I'm going to try the guess and check method again to see if I can just kind of figure it out. So I know that these two terms in the first front of my binomials have to multiply together to equal 9x squared. So I'm just going to try 3x and 3x because they do multiply together to equal 9x squared. That line underneath looks a little funky. All right, so no lines underneath, just 3x and 3x. then I have a 25 here. So I'm guessing again that these two numbers here and here are going to be 5 times 5. So these two terms have to multiply together to equal 25. A positive 25 though, which means these signs have to be the same. And because this is a positive here, the middle term is positive, which means both signs have to be positive. So the positive times the positive gives me a positive 25, and then my middle term is positive, so that these have to be positive also. So now let's check the 30. So if I multiply the outside terms together, the 3x times the 5, I would get a positive 15x. If I multiply by inside terms together, I would get another positive 15x, which does combine to give me the positive 30x. So this does work. And again, we could rewrite it because they're identical. You could rewrite it as 3x plus 5 in parentheses squared. So that's just another way you can write it. Okay, moving on to the next example. So problem D has 4 terms. One method of solving or factoring things that have 4 terms is by grouping. So I'm going to try factoring by grouping and see if it works. So with factoring by grouping, you're going to separate the first 2 terms from the second 2 terms. And I like to do this with just a little squiggly line here. Make sure that this sign is part of your third term. Then look at the first 2 terms only and ask yourself, what's the greatest common factor between those 2 terms? Well, both of them could be divided by 3, and both of them have x to the second power, at least to the second power. And then to figure out what's left inside, I would divide 18 by 3, which gives me 6x to the third. Take out x squared, or divided by x squared would give me x. I've got my minus here, and then 3x squared divided by 3x squared is just going to be 1. So now I go to the other 2 and ask myself, well, what's the greatest common factor I can factor out of those 2 terms? Well, they're both even, so I'm going to factor out a positive 2. Now you have to put a sign here to make sure that what you've written here is equivalent to what you have written above it. So when I divide the 12x by 2, I get 6x. And when I divide the negative 2 by 2, I get a negative 1. So if I were to multiply this back together, if I were to multiply the 3x squared times the 6x, I would get 18x to the third. 3x squared times negative 1 is negative 3x squared. 2 times 6x does equal 12x, and 2 times negative 1 does equal 2. So we have equivalent expressions here. Well, now is the hard part of factoring by grouping. Think of these 2 things, these groups, as terms. So if this is one term and this is another term, what do the 2 terms have in common? But instead of terms, they're groups. So if this is one group and this is one group, what do the 2 groups have in common? The 6x minus 1. So just like you factored out the 3x squared and the 2, we're going to factor out the 6x minus 1. So when you factor that out and you divide that 6x minus 1 out, you're left then with 3x squared plus 2 to put in the other parentheses. Now it doesn't matter what order you put these in. You could also have written the 3x squared plus 2 first and then the 6x minus 1. So that would be the same thing. Okay, so again, I like to check. So if I were to multiply the 6x times the 3x squared, I would get 18x to the third. If I took the 6x times a positive 2, that would give me my 12x. If I took the negative 3 times x squared, that would give me a negative 3x squared, and then the negative 1 times 2 does give me a negative 2. So I know for sure that these are the factors of that polynomial, and they cannot be factored anymore. Moving on to example E. So in example E, separate these. You're going to, first of all, look for a common factor. So both of them have a common factor of 3. So I'm going to factor that out. And when I divide each of these terms by 3, I'm left with w squared minus 4. Well, w squared minus 4 is a difference of 2 squares. So that can be factored again. So the 3 is going to stay out front, but your w squared minus 4 is going to factor just like problem A did here, where we took the r squared and we factored it into r and r, but the w squared is going to be factored into w and w. And just like we took the 121 and factored it into positive 11 and negative 11, this negative 4 is going to be factored into a positive 2 and a negative 2. And it does not matter whether you put the negative 2 first or the positive 2 as long as they are different. So this is our factored form now of the w squared minus 12. And then letter F is the same type of problem. It's just another example. 4 could be factored out of both terms. So if I factor out a 4 from the 16 and from the 4, I will get 4x squared minus 1, which again now gives me a difference of squares. So that 4 that's out front just stays there. And then take your square root of your 4x squared, which gives you 2x and 2x. The square root of 1 is 1 and 1, but in order for it to be negative, 1 has to be positive, 1 has to be negative. And if you multiply this back together, you would get what you started with. So these are the factors of 16x squared minus 4. And we have factored completely. Letter G. So in letter G, we have a basic trinomial. I call it a basic because there's a leading coefficient of 1. So when you have a leading coefficient of 1, and it is factorable, I like to set it up right away with the 2 parentheses. Your a squared is going to factor into a and a. And then now I'm looking for 2 numbers here and here that will multiply together to equal 24. But because this is a negative 24, your signs are going to have to be different. So when you add numbers that are different signs, a lot of times we have to think subtract. So if you have, for example, a negative 7 and a positive 3 added together, you would get a negative 4. And the way that you would get that is by subtracting the 7 and the 3, but you keep the sign of the larger value. So when we're factoring, I like to add, if there's a negative here, instead of saying what 2 numbers multiply together to equal 24 and add up to 2, because this is negative, I'd say, I think in my head, 2 numbers that multiply together to equal 24 that subtract or have a difference of 2. So that makes it easier for me to think of my 2 numbers, 4 and 6. Now once again, because this is negative 24, one of these signs is going to have to be positive and one is going to have to be negative. But in order for these 2 numbers to actually add up to a positive 2, the larger number is going to have to be positive and the smaller number is going to have to be negative. So now if you multiply these together, you do get a negative 24. If you add them together, you do get a positive 2. So these are the correct factors of a squared plus 2a minus 24. Letter H is very similar. It's another basic trinomial because you have a leading coefficient of 1. So again, I'm going to jump right into my 2 binomials. The c squared is going to factor into c and c. And then I'm looking for 2 numbers that multiply together to equal 25. But because of the plus here, and my signs have to be the same, I think to myself they have to add up to 10. So 2 numbers that multiply together equal 25 that add up to 10 are 5 and 5. Again, because this is a positive 25, these signs have to be the same so that when you multiply them together you get a positive. But in order for them to add up to a negative 10, they're going to have to both be negative. So the negative times a negative gives you a positive, but the negative plus the negative gives you a negative 10. So these are the factors, and because they're identical, you could rewrite it as a binomial squared. So c minus 5 squared, or just c minus 5 times c minus 5. So that's our review of factoring. And that is the end of the first lesson. So the next lesson will be geometry and measurement if you want to stay tuned for the next video.